Okay, just a heads up. Exam 3 is a week from Wednesday. Okay, so that would be the 24th, I think, April 24th. I'll talk more about topics and stuff as we get a little bit closer. Definitely circular motion will be on there. We'll see how far we get with conservation laws. So topics are to be determined. Anybody have any homework questions you'd like me to go over? Okay. Let's do a problem, and I'll give you a little time to try to think your way through it. Remember last time we started doing conservation of linear momentum? So let's say we have these two little carts. When they collide with each other, these latches are going to latch and they'll have the same velocity after. Let's say this one's 1 kilogram and this one's 0.5 kilogram. And let's say that before the collision, this one's moving at 1 meter per second and this one's moving at 5 meters per second. Okay. What's the shared velocity? So remember, they're going to latch. So whatever velocity one has, the other one has too. What's the shared velocity vector of the carts after the collision? Okay, so first of all, if you see a problem like this, how do you know that this is a linear momentum problem? Anyone remember? I mean, I know this was on Wednesday, and so it's been a while. I'm sort of just trying to jog your memory. But anything that says anything about a collision, or you identify something in it as a collision, you know that for at least that part of the problem, you're going to use conservation of linear momentum. Okay? And if there's no collision in the problem, then you're not going to use this. It's really just that simple. Okay? And so remember what conservation of linear momentum says is first you have to figure out if there's any net external force besides the force of the things running into each other. Okay? So the first thing you have to ask yourself is, can I use conservation of linear momentum? So is the net external force on the system 0? Okay. Remember, that doesn't mean that there are no forces acting on it. That wouldn't be the case here. Weight is applying a force to both of these things, and the ground is applying a force to both of these things. But if these are rolling at a constant speed and they're not turning, then there's no acceleration and the net force is equal to 0. Okay, so that is what sort of the way you want to think about whether there's a net force on these or not. So there's no net external force. remember, we're not talking about the forces the two apply to each other. Those are not included in this. So that means we can use conservation of linear momentum. And conservation of linear momentum, if the things stick together after the collision, says this. It says the mass of the first one times its velocity plus the mass of the second one times its velocity. This is before the collision. Is equal to the sum of the two masses times their shared velocity after the collision. Okay, so we're just going to plug these values in. If we have a coordinate system that's, our usual coordinate system, then the mass of the first cart, the one on the left, times its velocity before the collision. It's moving in the positive x direction, so that's 5, 0. Plus the mass of the second body times its velocity before the collision. Is equal to the combined mass times the shared velocity vector after the collision. And now we just have two equations for two variables and we can solve it. We have 5 plus 0.5 is equal to 1.5 Vx. So 5.5 is equal to 1.5 Vx. And so Vx is equal to 3.6 repeating. The y equation says 0 plus 0 is equal to 1.5 Vy. So Vy is 0. And altogether, this says that after the collision, the velocity is 3.60. Or in other words, its velocity is that direction with a magnitude of 3.6. Okay? Any questions about that? Let's do another one. So all of the examples I've done so far, all the motion is in the same direction. Let's do one just so you can see that it doesn't have to be that way. So let's say you have two objects that are moving before the collision. This one is moving this way at 10 meters per second. And let me make it so I can put the mass in there. Let's say this is 2 kilograms. Let's say this angle is 30 degrees. And it runs into a 1 kilogram object that's moving this way at 5 meters per second. If these stick together after the collision, what's their combined velocity after? Okay, let me give you just a couple of minutes and see if you can sort of, I know you haven't thought about this for a while, but see if you can figure out how to turn this into the form of the conservation of linear momentum. Okay, and then I'll go through it. So in this case, these two things aren't moving in the same direction, but the approach is still the same. You just have to come up with the vectors for these two velocities before they collide. For this first one, the one on top, the 2 kilogram, to come up with that vector, if this is the coordinate system, and we have a vector with a magnitude of 10, and this angle is 30 degrees from the x-axis, to go counterclockwise to this, you'd have to go around like this, and it would be 360 minus 30, so 330 degrees. You also could just go clockwise and call it negative 30, and you'd get the same answer. But so this velocity is equal to 10 times the cosine of 330, 10 times the sine of 330, and that is 8.66, negative 5.0. The other one is just moving in the positive x direction, so that's just going to be 5, 0. So now conservation of linear momentum says 2, the mass of the top one, times its velocity before the collision, plus the mass of the second one times its velocity vector, is equal to the sum of the masses times the velocity after the collision. And so you get, for the x equation, 17.32 plus 5 is equal to 3vx. And you get that Vx is equal to 7.44. And then for the y equation, 2 times negative 5 is negative 10, plus 1 times 0 is equal to 3vy. And so Vy is equal to negative 3.3 repeating. So altogether, these say that after these two things combine, after they collide and stick together, the velocity vector is 7.44 in the x direction, negative 3.3 repeating in the y direction. And if you want to draw that, you can think of, plotting a point, like you can sort of imagine this coordinate system. Plot that point, and it would be somewhere like this. Then that's the head of the vector when the tail is at the origin. Okay? Any questions about that? So this is a case where the direction they end up afterwards isn't the same as the direction before. This sort of relates to how you play pool and stuff like that, You're using conservation of momentum to try to figure out where you're going to get these balls to go afterwards. The difference, of course, is pool balls don't stick together, so you'd need some other math in there, but that's sort of the idea. Okay. So now the bigger topic in conservation laws is conservation of mechanical energy, and we're going to start talking about that now. And remember, conservation of mechanical energy, if you're looking for a kind of problem where we're going to use this, it's going to be problems where you're relating an object's location to its speed. Okay? If it doesn't help you to relate an object's location to its speed, then conservation of mechanical energy can't help you. Okay? And I'm going to give you the punchline first so you know sort of what we're working towards. The equation itself is pretty simple, but then I'm going to go back and define some things, and it'll take a little while. But here's where we're going to end up. If there are no changes in an object's thermal energy, electrical energy, magnetic energy, okay, so all these things, there's all these ways that an object's energy can change. You know, it has to do with temperatures, electricity, all this stuff. Well, we're not talking about that stuff. So if we're thinking of objects that don't have any of that really going on, like an object just rolling down a hill, you know, or an object that you pull back a spring like a pinball game and shoot this object. Okay, there's no changes in electricity or magnetic stuff or heat or anything like that in an object like that. In that case, oh, and one other requirement. So if there's no changes in all these different kinds of energy, and the only energy change comes from what's called potential energy. Then the object's potential energy, I'll call that U, plus the object's kinetic energy, I'll call that T, has to stay a constant. It doesn't change. The sum of those two. So this is called potential energy. This is called kinetic energy. And that's not saying that neither one of these changes. You can get changes in potential energy, but if the potential energy goes up, the kinetic energy has to go down. And if the potential energy goes down, the kinetic energy has to go up. okay? And we can calculate changes in speed based on this relationship, okay? Okay, so we're not dealing with electricity, magnets, temperature changes, phase changes, anything like that. We're not talking about going from, you know, a liquid to a solid or anything like that. We're just talking about mechanical things happening, mechanical energy, okay? And if the only energy changes come from changes in potential energy, then these two have the relationship where you lose one, you have to gain that same amount of the other one. Okay. So now we're going to spend some time defining some of these things, and it'll be a little bit of a long process. But notice how simple that equation is once we get back to it. The simplicity of it is what makes it useful sometimes. Okay, so first we have to define a few things. We have to define work, kinetic energy, conservative forces, and potential energy. And once we've defined all those things, then we can start putting them into an equation and calculating relationships between where an object is and how fast it's going. Anybody have any philosophical questions or anything yet? Anything about any of this energy stuff? It's going to feel very different than all the working with vectors we've done in the past. And in a way, that's going to be the nice thing about it, because it's the thing that makes it so simple. But in a way, it also, you know, makes you sort of think about things in a different way, a new way. Okay, so the first thing I'm going to define is work. And I have to define work because I said that in order for this equation to work, to be valid, the only energy change, and that energy, forget that. I guess I haven't said anything about work yet. Okay, so let me just define this. It'll come up when we start talking about potential energy. Work is a change in energy caused by the application of a force. If an object's displacement from instant 1 to instant 2 so from instant 1 to instant 2 is the vector d. Do you remember what the definition of displacement is? That isn't one that we've used too much, but we've used it a handful of times. Anyone remember what the definition of displacement is?
The space between the point and.
Yeah, that's a good way to think about it. It's the definition, you can think of it, if you want to calculate it, as the position at the later instant minus the position at the earlier instant. And it's just the vector that goes from the starting position to the ending position. So it's a vector from the position at instant 1 to the position at instant 2. So if the object's displacement is this vector d, and if the force applied to the object that whole time is F, then the work done by that force is, so we'll call it capital W, and it's equal to the x component of the force times the x component of the displacement plus the y component of the force times the y component of displacement. There's a name for that calculation, and it's called the dot product. So you could also write that like this with a, it looks like a multiplication symbol with a dot. And so let's do a quick example. If an object drops from a height of 5 meters to a height of 0, what's the work done during that time by gravity? Okay. Well, first we have to calculate the displacement. And the displacement vector is going to be the position at the later instant minus the position at the earlier instant. At the later instant, the position is 0, 0. It doesn't matter what that x position is. All it's doing is just dropping straight down. So we'll imagine our origin right underneath where this object is falling. So that's the position at the later instant. What's the position vector at the earlier instant? Yeah, 0, 5, right. And so the displacement vector is 0, negative 5. Or in other words, if you want to visualize it, it's a vector pointing in the negative y direction with a magnitude of 5 meters. We're looking for the force done by gravity. So what's the force vector of the object's weight? Oh, let's give it a mass. Let's say that it has a mass of 3 kilograms. So over this whole time, the force of gravity stays the same. What is that force? It's downward at 3 times 9.81, right? So that's going to be 0, negative 29.43. Again, this is just straight down with a magnitude of 29.43 newtons. Now that we have the displacement vector and we have the force vector, we can calculate the work. So the work is the x component of the force times the x component of the displacement plus the y component of the force times the y component of the displacement and this comes out to be 147.15. What are the units? We have newtons from the force and meters from the displacement. Okay, so those are units. It turns out that when we're talking about energy, we have a name for newtons times meters. So the units for any type of energy are newtons. Sorry, these are the SI units. Let me write this as units of force times units of length. And if you want to break it down more than this, since units of force can be made out of units of mass, length, and time, this also can be units of mass times units of length squared over units of time squared. So for SI units, that is newtons times meters, which is the same thing as kilogram meters squared per second squared. And we give that its own name, which is joules. And we'll denote that with a capital J. So what that says is that 147.15 Newton meters, you can also write as 147.15 joules. Okay, we figured out that by doing this calculation, that as an object moves down, the work done by gravity is positive, right? We got this positive value of 29.43. What we're going to see is that if, the work is positive, 147.15. If we have positive work, it means that energy is being added to the object. And if we have negative work, it means that energy is being removed from the object. Okay? So work is, like a positive value of work is an increase in energy caused by the application of a force. negative value of work means a decrease in energy caused by the application of a force. Okay, the intuitive result here, the thing I want you to keep in your mind as you think about values for work, is first, if the force vector is within 90 degrees of the displacement vector, so we're talking about like you could have a force going this way while the displacement is going this way. That angle is less than 90 degrees between those. Then work is positive. And the object's energy increases. Okay? Second, if F is more than 90 degrees apart, more than 90 degrees from the displacement vector, that's a case where, you could say you have a force like this and a displacement like this. If you measured those with a protractor, they're more than 90 degrees apart. Then the work is negative. And that means that the force removes energy from the object. There's one more case. What do you think that's going to be? If it's exactly 90 degrees apart, if they're exactly perpendicular. So if F and D are perpendicular, then the force causes no change in energy. The work is equal to 0, and the force doesn't change the object's energy. What does it mean for an object's energy to change now when we're talking about mechanical energy? So this is something important to keep in mind when you're thinking about this. An object gaining energy means it's speeding up. And an object losing energy means it's slowing down. Okay, so let's think a little bit about how this works. Imagine a cart moving to the right as a force is applied to it. Okay, so here's the cart. And let's say at instant 1, it's here. And at instant 2, it's here. Then between instant 1 and instant 2, the displacement looks like this. Okay, that red is the displacement vector. If you're going to apply the same force over that whole motion, what direction would you want to apply that force to make this cart speed up? What? To the right, exactly. Can everybody see that? I mean, if this thing's already rolling and you want to make it go faster, if it's going from here to here over this interval, then you'd want to push on it that way. And that's a force going to the right. That's how you increase the energy. Okay. If you wanted to slow it down, you'd get in front of it and push back to the left. Okay, and that would slow it down or stop it. And then if you wanted to apply the same force, the same magnitude of force, and not have it affect the speed at all, the way you could do that is by applying a force that doesn't do anything side to side, like putting another little weight on top or something. That would put a force down on it. So that force would be perpendicular to the displacement, and it wouldn't affect its speed at all. So do you see the connection between this and what I said about whether these force and displacement are within 90 degrees, more than 90 degrees, that kind of thing? Okay, well, let me write this down. So, okay, so the displacement vector is to the right. So 1, to speed the object up, you'd want to apply a force this way. Okay? That force, since it's within 90 degrees of the displacement vector, the work would be greater than 0. And that means that energy increases. Well, that's what it means when it speeds up. The energy increases. To slow the object down, you'd apply a force opposite the displacement. That means the force and the displacement vector are more than 90 degrees apart. That means that the work is less than 0. And that means that the energy decreases. to keep the speed the same, you could imagine applying a force straight down. Then force and displacement are perpendicular. That means that the work done by that force is equal to 0. And that means that the energy stays the same. Okay? Well, so far I haven't really defined what this energy is that goes up when the thing speeds up and goes down when it slows down. But that's the next thing I want to define. I gave you this list of definitions we have to do. I told you about work, so how a force can increase or decrease energy. Now let's talk about energy itself. So the energy that we're talking about is kinetic energy. So let M be an object's mass. And V be the object's speed. Then the kinetic energy it's what we're calling capital T, and it's equal to 1/2 times the object's mass times its speed squared. If you have the object's velocity vector instead of its speed, you can do this exact same calculation as T is equal to 1/2 times the mass times the x component of velocity squared plus the y component of velocity squared. Okay, here are some things to notice. So the first one is the relationship between speed and energy. As an object's speed increases, its kinetic energy goes up. Okay, so you can, in your head, you can relate speed and energy that way. The second one is, notice that this is not a vector. So kinetic energy is a positive number not a vector. So energy doesn't have any direction. We're not doing this like a vector calculation. Energy doesn't have a direction. Okay, well, let's do a quick calculation. So, for example, let's say that a car has a mass of 1,000 kilograms and a speed of 50 meters per second. What's its kinetic energy? Just plug those numbers into the formula and you get a kinetic energy of 1/2 times 1,000 times 50 squared and you get about 1 million, 1.25 times 10 to the 6th joules. What about like a turtle? A turtle has a mass of, I guess it depends on the turtle, let's say 0.1 kilograms. And a speed of 0.5 meter per second. The kinetic energy of the turtle is 1/2 times 0.1 times 0.5 squared. And so that is 0.0125 joules. So in our daily experience, there's a pretty big range of values of kinetic energies, Anybody have any questions about the definition of kinetic energy? Okay, let's go back to this equation. When I introduced the equation that we're going to use, I said that in order to use this equation, the only energy changes could come from potential energy. So now we're going to talk about conservative forces, and relatedly, what are the situations where you have such a thing as potential energy? Not all objects have potential energy. Not all forces have potential energy. So Let's talk about a certain kind of force called a conservative force. Okay, conservative forces are important to us because they're the only type of force with potential energy. They're the only forces with potential energy. The reason that's important is because, remember, conservation of mechanical energy only works when work is done by potential energy. Okay, so this idea of conservative forces is going to be really important. It's going to be important that certain types of forces we deal with have to be conservative forces. The definition of a conservative force is a force is conservative if knowing an object's location is enough information to know the force applied to it. You know, if knowing an object's location tells you the force applied. Okay, so let's think of what kind of forces there are this way. If you just think about random forces, you know, shaking someone or a friction force or something. There are a lot of forces out there. Most of the forces out there are not conservative, but there are some important ones that are. So let's think about what those are. Okay, so first of all, let's think about gravity. Say that you know the mass of this calculator, okay? So 0.1 kilograms or something. And now say I tell you where it's located. Can you tell me what the force is that gravity applies to this calculator? Well, okay, so it has a mass of 0.1 kilograms. If I tell you its location is here, do you know the force gravity applies to it? Yeah, you do. In fact, that's even more information than you know. But it does satisfy the requirements of a conservative force. So if I tell you it's here, you know that gravity is applying a force of 0.1 times 9.81 down. Right? It really didn't even matter that it was here. And if I tell you that it's here, the gravitational force is still the same, 0.1 times 9.81 down. Okay? So it meets that requirement. If I tell you the location, you can tell me the force. So gravity is a conservative force. Okay? Let's think about the only other conservative force that we're going to do calculations for. Imagine that this thing, we know the mass of it, and it's attached to the wall by a big spring, okay? If you know how stiff the spring is and stuff, and I told you how far you'd stretch the spring, so I told you the location of this thing, you could calculate how much of a force the spring is applying to it, okay? If I told you the object is here, then based on the fact that it has to have stretched this much, you could calculate the force. If you pulled it all the way to here, that force would be bigger, you know? If you compressed it to here, that force would be in the other direction. So the force of gravity and forces applied by springs are both conservative. So gravity and the force applied by a spring are both conservative forces. Now let's think about a couple that are not conservative. So first of all, let's think about the normal force, okay? So the normal force that the table is applying, pushing up on this calculator to keep it from sinking into the table, okay? If I tell you the location of the calculator and its mass, is that enough to know the normal force? At first thought, you might think like, well, yeah, because it has to balance the weight. But notice that it could be at this same location, and I could push down on the top of it with my finger. That makes the normal force increase without changing the location. And so a normal force is not conservative. What about a friction force? Well, that maybe is even a little more obvious that it's not conservative, because if the calculator reaches this point while it's sliding this way, the friction force has to be opposite that. If the calculator reaches that point sliding this way, it has to be opposite of that. So normal forces, friction forces, let me write those down. So normal force, friction force, let's put cable tension in here. Are all, you could come up with a million more of these, but these are all non-conservative forces. If a force is conservative, it has a potential energy function. So these things, normal forces, friction forces, cable tension forces, there's no such thing as potential energy for those. But for springs and weight, there is such a thing as potential energy. For the two conservative forces we'll see in this class, the first one is weight, you know, the force of gravity. The potential energy function due to gravity is the mass of the object times 9.81 meters per second squared times the object's height. And notice that this is positive, this G, okay? When we have G values that are negative, it's just a direction. The value is a positive 9.81. And then this H is the height. The other one that we're going to deal with is spring forces. And the potential energy for a spring force, I'll call it USPR, is equal to 1/2 times K times X squared, where K is the spring stiffness, and X is how far the spring is deformed from its resting length. Okay. There's a relationship between potential energy function and the work done by a conservative force. So really, this is the whole reason why we care about potential energy. So there's a relationship between the potential energy and the work done by that conservative force. And that relationship is the work done by the force is negative change in the potential energy. Okay? So if an object's potential energy goes up, then negative work is done and energy is taken away from the object. If the potential energy goes down, energy is added to the object. So let's think about that in terms of gravity. Okay, so like for example, think of an object that starts at a height of 1 meter and ends at a height of 4 meters. Calculate the work done on the object by gravity. Well, we have two ways to do this. One is we could use a displacement vector and a force vector. We know that the displacement, at instant 1, so the position at instant 1, we can think of as 0, 1. The position at instant 2 is 0, 4. And so the displacement vector is 0, 4 minus 0, 1, or 0, 3. Again, let's make sure this object has a mass. Let's make this 2 kilograms. Okay, what's the force that gravity applies to the object over that interval? It's 0, negative 19.62 newtons. And so the work done by gravity over that motion is 0 times 0. That's Fx times dx plus Fy, negative 19.62, times dy. And so we get negative 58.86 joules. But we can do the same calculation using potential energy. At instant 1, we're going to use the potential energy function for gravity. This one. These two are both going to be important to us in this class. But so we're using mass times g times h. So at instant 1, we have a mass of 2 times 9.81 times a height of 1. So we have 19.62 joules. At instant 2, we have a mass of 2 times 9.81 times a height of 4 meters. And this is 78.48. The work is the negative change in potential energy. So it's negative U2 minus U1. And you get negative 58.86. This way of doing it is hard in a lot of cases. This way is always easy to do. Okay. So we've almost finished all the definitions we need to go into conservation of mechanical energy, and we'll get to that on Wednesday. Yeah?
Couldn't you also do U1 minus U2? The same thing?
Yeah, you could write it that way, sure. Yep. Any other questions? Okay, I think there's a problem or two I can give you on this sort of intermediate stuff, but then next time we'll get to where we can do really all the problems.